For our next speaker, we have Mateo Galdeano from Oxford, and he'll tell us about superconformal algebras for generalized connected sums. Take it away, Mateo. Thanks.
Yes, thank you very much. Thanks for the introduction, and thanks to the organizer for the opportunity to speak here. I'm very happy to be here telling you about these superconformal algebras and generalized connected sums. And well, that's what I'm going to do here. First, I'll introduce a little bit the thing. I will tell you what I mean by these superconformal algebras and these generalized connected sums. And then I'll do some stuff with it, and hopefully we'll get to see some very cool applications and a nice interplay between geometry and physics that is going on here. So first, to introduce and motivate a bit what I'm doing, let me talk about the setup. So I want you to think about string theory. Typically, you can think of some type 2 theory. And we are going to take some sigma model perspective. So we're going to have our strings moving on the target manifold. And I want to look into the superconformal field theory in the worldsheet. And the key here is the interplay between the target compact manifold, which has typically some holonomy group G, and the worldsheet itself. So for the rest of the talk, whenever I write something related to the worldsheet, I put it in this green color, and everything related to the target manifold will go in this blue color. And yes, so what is the relation between these two things? What can we learn about one aspect or the other? Well, the most important thing is this relation that I have here, and that I will explain more detail later. That if we have some covariantly constant forms in our target manifold, we immediately can think of some operators in our worldsheet superconformal algebra. And for our purposes, what this is going to mean is that when our manifold has some holonomy group G, this is going to correspond to some extension of the Virasoro algebra. And this interplay is going to be very useful and very rich. In particular, I'm going to focus today on manifolds which are constructed in a very special way, which are these generalized connected sums, which are some spin 7 holonomy manifolds. And the special thing about these manifolds is that they are constructed by gluing two different pieces. So what we are going to see, and I want to show to you, is that precisely this piecewise geometry that we have can be also translated to the realm of the worldsheet algebra in terms of some inclusions, and in particular some inclusions in the shape of a diamond. And once we have this set up, we can learn some things on both sides about the manifold and about the physics that is going on. In particular, I will talk about some very cool applications to spin 7 mirror symmetry. Okay, let me then motivate this superconformal algebra in the worldsheet and how do they arise. So thinking of the sigma model that I was mentioning before, we can think to start with at a classical level. And I want to talk about what I call here the Haupt-Papadopoulos W symmetry, that essentially shows how covariantly constant forms correspond to some worldsheet symmetries and conserved current at classical level to start with. And the best thing to see this is through an example. So if you write the n equals 1,0 sigma model with some target manifold, the simplest example possible, and you write here the action. Then when the target manifold has some covariantly constant form, P form in particular, what you can do is construct these symmetries and currents that I was talking about. And the way you do it, I have it here in the next slide, I'll show it to you. The important thing to notice here is that we are taking something which is in the target space, and we are using it to define something on the worldsheet. And here's where this nice connection is going to arise. So the explicit expression is not important. The important thing is how this relates the two things. And well, this was at classical level, but we're going to think about quantum level. So after quantization, these currents are going to correspond to some operators on the worldsheet. And this is precisely the relation that I was motivating earlier. that when we have covariantly constant forms, we can think of operators. And this is my first take-home message. And if after this talk you only get this out of it, I'm already happy. This is already something very interesting. But please don't disconnect right now because there's more stuff coming up. So now I have to say that, okay, first, don't get scared about this table. It's here just for completion. But what we can do with these operators, as I was saying, is to extend the Virasoro algebra to have some extended algebra, essentially, which is not just Virasoro, but we also have some additional operators. And to motivate this, I'm just going to go over one of the rows in this table. So for example, in the case when the target space is flat, for example, a circle, you have some covariantly constant form, which is just essentially the coordinate. And through this procedure that I was explaining before, you can associate some generators that actually generate a free algebra. So in the case of the flat space, we just have a free algebra. And of course, depending on the holonomy group of your manifolds, you're going to have different forms. For example, you might be familiar with the Calabi-Yau case, where you have the holomorphic volume form and the Kähler form. And there are some associated operators and some associated algebra. The details here are not important. What is important is that for every special holonomy manifold, we have some algebra that we can associate. And this gives us a dictionary, which is essentially the most important thing here. So every time that we have something in geometry, we have some manifold with special holonomy, we can think of an extended algebra in the worldsheet. So this is just to set the notation. Just for the Calabi-Yau manifolds, the associated algebra is called the Odake algebra. And for the G2 and spin 7 holonomy cases, the associated algebra is called the Saakashvili-Vafa algebra. This is the notation, but do not worry because I'll remind you of this notation later as we move on. Okay, so this is the worldsheet part, let's say, how we relate the two things. Now let me talk about the manifolds that I want to look into, these generalized connected sums. Well, let me first give a brief summary of what they are, how they appeared. Now you have to bear with my drawings, which are not amazing, but I promise you they're going to be helpful. So these generalized connected sums were first introduced by Andreas Braun and Sakura Shakotameki some years ago. And these are manifolds of spin 7 holonomy. The truth is that they are believed to have spin 7 holonomy, but there is not a full mathematical proof of this fact. And there's only, let's say, physics proof of this, which for us should be enough. And they are built, these manifolds are just a generalization of the G2 twisted connected sum that maybe you're familiar with. And the idea, and you can see here in the different colors, is that we are going to glue together two different manifolds, as I was anticipating earlier. These two manifolds are going to have some common region, and we are going to use that to glue them. And we're going to get a compact spin 7 holonomy manifold. Okay, so what are the ingredients that we need to build this up? The first ingredient that we need is what is called an asymptotically cylindrical Calabi-Yau fourfold. So the way I want you to think about this is think of a Calabi-Yau fourfold, which is not compact, so it's an open manifold. And there is some special direction in your manifold, which in the picture is going there to the right, such that if you follow that direction, in some limit, the Calabi-Yau 4 can be rewritten as a Calabi-Yau 3 times a cylinder. This is what the picture tries to show and what I'm representing here. And the important thing is that there are some asymptotic relations between the forms that we have in our manifold. So the holomorphic volume form is written in a particular way in terms of the Calabi-Yau 3-fold and the cylinder. Okay, this is one of the manifolds. For the other manifold that we want to glue, we're going to take something slightly different, which is an asymptotically cylindrical G2 manifold times a circle. But the idea is exactly the same. We have a very particular direction, and in this asymptotic limit, we actually have, again, a Calabi-Yau threefold times a cylinder. Good. Now, as you might have realized, both of these manifolds have the same asymptotic region. So what we're going to do is to patch them together to make a single compact manifold. And this is essentially the last step. Now, when we have glued these two things together, what we realize is that we can define some spin 7 four forms in both sides. And if we have done the gluing correctly, these spin 7 forms patch together nicely and give us a well-defined four form. And the idea is that then one can do some analysis and some tricks, and it should be possible to deform this in such a way that you get some spin 7 holonomy manifold. Nice. So these are the manifolds that we are going to use. And I wanted to stress this because what you might realize is that this is a bit special, right? It's not just a generic spin 7 holonomy manifold. It has a very particular structure, and different pieces behave differently. So what we wondered, we were wondering in this paper together with Marc-Antoine, is if we could actually get something more out of it. And this is indeed the case. And what I'm going to show you now is how to do this, how to exploit this extra structure to get a nice relation in your worldsheet. So this is what I call the diamond, and it'll be obvious very soon why I call it the diamond. So as I was saying, the question is, how can we use these geometric data in pieces? Well, what we are going to do is to use this dictionary that associates an algebra to each particular geometry that I introduced before. So for each, let's say, open patch of the manifold, we're going to have a particular algebra. Now, as I was explaining earlier, these different pieces of the manifold are not completely disconnected. There are some asymptotic relations between the forms that ensure that everything patches up nicely. And these geometric ideas are actually going to give us some ansatz for some algebra inclusions. So to each part of the manifold, I'm going to associate some algebra, and just from the geometry, there's going to be a very natural inclusion of the different algebras. And this is essentially what we're going to construct. The algebras can be arranged as a unique diamond of inclusions. It's going to mimic this geometry. And this is what I have in the next slide. And it's the most important slide in the talk, probably. So let's look at it a bit carefully. So here on the left, you see this manifold, this generalized connected sum manifold that I was introducing before, with the Calabi-Yau fourfold, the G2 manifold, and this middle region with the Calabi-Yau threefold and the cylinder. And in the global structure is a spin 7 structure. Now, as I announced, I just associate to each part the corresponding algebra following this dictionary. So to this Calabi-Yau fourfold, I associate an Odake 4. To the G2, I associate a Saakashvili-Vafa G2. And here I have an Odake 3 and a 3 squared because I have a cylinder here. And to the total spin 7 structure, I associate the Saakashvili-Vafa spin 7. Cool. So this, you see that the colors match. Like this is just a complete matching. And the way in which this, for example, this Calabi-Yau fourfold is embedded into the spin 7 is precisely captured by this algebra inclusion. These algebra inclusions come just from geometry. Like geometry tells you exactly what you need to do here. Of course, checking that these things work is not trivial. We had to work a little bit to make sure that everything patched up nicely. But it was very satisfying to see that that was indeed the case. And now, once we have this, you might wonder, well, what do we do with this now, right? Like, can we use it to get some information? And the answer is yes. This is what I'm going to do in the rest of the talk. Just tell you what can you do with this. So the first thing I want to mention is something that I was talking about earlier, and it's that these generalized connected sum manifolds actually don't have a mathematical proof yet that shows that they exist or they work correctly. So the interesting thing about the existence of these diamond of algebras and how nice it works is that we believe, and we strongly believe, that this hints towards the existence of these generalized connected sum constructions in full generality. Something that maybe I haven't stressed enough is that this diamond of algebras is very, very general. We are not saying much about the particular string theory compactification that we're taking, like what we're doing with our fluxes, what we're doing with our thing. This is like a very general feature. And as a result, the fact that something so general exists, I think it hints towards the existence of these manifolds as something that is well defined. So our result can be regarded as some proof of existence from the point of view of worldsheet string theory for these manifolds. Then there's another interesting question that this diamond makes explicit, and it's well, here I presented to you a bit of an altered version of the diamond, where I've introduced here the intersection between the lateral tips of the diamond. So one might wonder, okay, suppose that we believe that these manifolds exist, and now we want to see if they give some well-defined spin 7 holonomy. You might be worried that, since these are constructed in a very specific way, maybe they would not be providing like a generic spin 7 manifold. Maybe there's some hidden symmetry that we are not seeing. Well, if that was the case, if the general construction had some hidden symmetry that we were not realizing about, this would be reflected in the diamond of algebras exactly like this. There will be, and the question would be if this intersection between the lateral tips would be equal to the spin 7 algebra or not. Meaning that if we actually have a larger algebra here, we have some extra operators, and this means that we have some extra preserved forms because of this relationship that I was talking about earlier. So a very natural question is exactly this one. Do we have the equality between the spin 7 algebra and this intersection? And this is actually a hard problem, something that we thought about, and it's hard because if you want to show it in full generality, you need to understand very well how the characters of the algebras work. And for these algebras, there's not a very well, for spin 7 it is, there is some work that has been done, but for the rest, there's very little in the literature. So we have to resort to some numerical computation. And this is what we did. We did some numerical checks, comparing the vacuum characters level by level between these two algebras. And up to a certain level, in these algebras, level 6, we find agreement, which is, I would say, like a non-trivial check that this equality holds, and actually these manifolds, again, are well defined. Cool. So this is maybe a bit on the more mathematical, theoretical side. And now I want to turn a bit into physics and talk about spin 7 mirror symmetry. So spin 7 mirror symmetry is something that maybe some of you are not familiar with. So let me first tell you what this is about. So if you're familiar with the usual Calabi-Yau mirror symmetry, in the most basic sense, this is essentially what we're going to do here as well. So we're going to say that two spin 7 manifolds are mirror symmetric if they give rise to the same physical theory after compactification. So we have two manifolds and we compactify and the theories are the same, then we say that these are mirror symmetric. Now, what does this mean in our language? What does it mean for us in terms of this worldsheet algebra that I was talking about? Well, it just means that the superconformal algebra has to be the same, because if the physical theory has to be the same, the algebra better stay the same, right? So if you want to think of two different manifolds and the existence of a mirror map between them, right? Imagine that we have two mirror manifolds and some mirror mapping geometry that is going from one to the other. And the level of the worldsheet algebra, what this would do, we just leave the algebra invariant. So it has to be an algebra automorphism. So this is very useful and very nice. We can rephrase mirror symmetry in terms of automorphisms of these algebras in the worldsheet. On the other hand, in geometry, you can think of this in this Strominger, Yau, and Zaslow approach. You can think of mirror symmetry as arising from performing some T-dualities in some torus vibration, which might be singular. And what I'm going to do now is to play with both things. I'm going to look at the algebras, and I'm actually going to find also a geometric interpretation of these. So,
Mateo, you've got 5 more minutes.
Perfect. Yeah, thank you very much. Yeah, plenty of time. Okay. So before talking about the spin 7 mirror symmetry, let me talk a bit about automorphisms of these algebras. So these are the algebras that I've been talking about all the time. You know, these Hodaki algebras, Tashvili-Baffa algebra, and each of them has certain group of automorphisms, right? So, for example, for the free algebra, which is the one corresponding to the circle, if you remember, there is a very natural automorphism that can be interpreted as T-duality in geometry. For the Hodaki algebra, which is the one of the Calabi-Yau manifolds, there is a particular automorphism. The explicit form is not important right now, but it corresponds to the geometric idea of mirror symmetry and these dualizations of some torus vibration. Now, even for G2, we also have some mirror symmetry map, but for spin 7, the only automorphism of this algebra is the identity. There's nothing else. So maybe after this, you will think that there's no spin 7 mirror symmetry, but that's actually not the case. The interesting thing is that even though we have an identity automorphism in the algebra, we're just not doing much. In geometry, something non-trivial might be happening. But of course, if you just have a generic spin 7 manifold and you're just looking at this algebra, there's not much you can say about it. Luckily for us, what we have is this diamond. So what we're going to do is look at automorphisms of the whole diamond. And something very interesting happened. When you look at the whole diamond, you find 4 different automorphisms that preserve the whole diamond. So you see that the action on each of the different algebras is a bit different, but all of them in spin 7 reduce to the identity. So even though when you look at the spin 7 manifold, it looks like they are the same map in the worldsheet, they're actually secretly not. You're doing different things in the different patches. So this is what we found. And then what we wanted to do is to actually see if all these possibilities were realized. So we just did this for an easy example. And the easy example to test these 4 mirror maps are the Joyce orbifolds. So a way to construct spin 7 holonomy manifolds is by resolving some singularities on an 8-dimensional torus, which has been quotiented in a certain way. The details are not very important. What is important is that some of these manifolds can be regarded as generalized connected sums if we pull them apart along one direction. So this makes it very easy to actually look at the diamond, because you have these torus coordinates, so you can find a free field realization of this diamond. And then one can take this Strominger-Yau-Zaslow approach that I was saying and think of mirror maps as performing T-dualities along the supersymmetric torus vibrations. And what we found is that all our mirror map candidates are realized in this case. I'm just going to show you one of them. So this is a drawing of the A3 map. The A3, let me go back for a second. It was the one here in the column. So I just copied that into a specific example. And you can see that actually all these map in the algebra corresponds to has some geometric interpretation. For example, I'm not going to go into a lot of details, but there are some dualization of some special Lagrangian fibers, for example. So you're taking some supersymmetric torus vibration and you're dualizing it secretly. So you don't see, when you don't look at the diamond, you don't see that this is happening. But when you consider the full diamond, you can actually understand what is going on. So this makes us propose that actually these mirror maps are valid for all GCS manifolds, even beyond the Joyce orbifold setting. And the reason is, as I was saying, that this diamond thing is completely general for these generalized connected sums. Okay, in my last minute, I want to just conclude. And the conclusion is very simple. There's like three main takeaways, I think. The main takeaway is, again, this picture. We can find some diamond that reproduces this geometry. And then it can be used to get some information. For example, to give more evidence of the existence of generalized connected sum manifolds, and also to produce some new spin-7 mirror symmetry maps. And spin-7 mirror symmetry is not, unfortunately, we don't know much about it. So this is quite interesting. Yes, and then, of course, there are future directions where you can take this. I've talked about diamonds for this spin-7 case, but there are some Calabi-Yau manifolds can be also built from two pieces, so you could think of doing that for Calabi-Yaus. And even for some more general constructions of geometry, I think this is something that we would like to do in the future. It would be very interesting to think about, or look at mirror symmetry in different contexts using this setting. Okay, I think I'm out of time, so just thank you very much. And if you have any questions, please let me know.
All right, let's thank Mateo for the very nice talk. Let's see, is there any question? Yeah, Craig?
Hi, yeah, this is a nice talk. So there's something I'm kind of confused about. So in the diamond, so I guess my question is, why are they both included in the same SV spin-7 at the bottom? So yes, where does the actual connected sum part of that, like the generalized connected sum, come into that statement?
Yeah, thank you. That's a very good question, Greg. I think the important thing about this is that in order to make sure that you have a well-defined global spin-7 manifold, you need to make sure that you have a well-defined form all over the manifold. So you have to be, when you make this gluing, you have to be a bit careful with your conventions and how you are defining things so that everything patches up nicely. And this is what this unique spin-7 is reflecting. The fact that there's a unique embedding of this spin-7 algebra in both of them is precisely reflecting that there's this unique nice patching that actually gives you the full spin-7 holonomy form. Does this make sense?
So I think so. So maybe there's an example which helps me. So if I do the same thing for the twisted connected sums.
Yes.
So now I guess at the top I would write OD2 because I would have a K3.
Yes.
Fiber, and then as the 2 in the middle, I would have OD3 on both sides because I have two collateral 3s, and at the bottom I'd have the SVG2. Is the point that there is now two unique embeddings, or I mean two inequivalent embeddings of OD3 inside of SVG2 or something like that?
Yeah. So the claim is that in this twisted connected sum case, maybe in that case it's even easier. Yeah, it's a bit different because the two sides of the diamond are equal.
Right.
But what is going on is that in this twisted G2 case, you have a very specific gluing map, right? If you remember about this, you need to do some hypercalibrate rotation. There's some non-trivial things. So it's a bit of the same thing in the sense that you need to choose like your two manifolds to be glued in a certain way so that this hypercalibrate matching gives you precisely a well-preserved G2 form over the whole thing. Yeah. And the diamond in that case precisely reproduces this. Like once you choose your conventions, you have these two algebras, which of course are the same algebra, but they're actually different embeddings inside the algebra at the top of the diamond. So they are not the same. And when you intersect these two different embeddings, in the intersection, what you find is this category of a G2 algebra. And this just that's the unique thing. Yeah.
I see. Okay. Yeah. Thank you. That's super helpful. Yeah. Thanks.
Yeah. Thank you. Very nice question, Craig. Yeah, thank you very much.
All right. Is there any other question?